for joining us, everyone. We have Chris here from the Water and Carbon Group, and we'll do a little presentation on PFAS and extracting it using foam fractionation. So we'll go ahead, Chris.
Abby, much appreciated, and thank you, Allison, as well. So yeah, I'm gonna get into the process of foam fractionation, kind of what that looks like and what goes into the process itself. A little bit of an overview of what I'm going to cover today. A little bit about PFAS itself. Talk about it from even a chemical structure briefly. A little bit on legislation and kind of what's going on from a federal standpoint as well as a state standpoint. A little bit about foam fractionation technology, and then the LEAF system specifically, which is the Water and Carbon Group's foam fractionation system. And then I want to give you guys a real example of what a foam fractionation project looks like and what a system looks like that's operating now. It's our Bethlehem, Pennsylvania project, as well as a rough idea on CAPEX and OPEX. And from there, we can get into some questions at the end. So a little bit about PFAS itself. I'm going to start off by using the word precursor that you may have heard before and what that actually means with respect to a PFAS compound. So when you think of the word precursor, kind of what goes with that is everything that's added on to a PFAS compound in a sense. And let's say you were to consider AFFF firefighting foam, which is loaded with PFAS, right? Companies like Johnson Controls, Tyco, 3M, all of these types of companies might have their own secret sauce in a sense on what their special type of AFFF is. It's their, like any type of product that you launch or bring to market, right? You're going to have product differentiation. Their differentiator is their secret sauce that they add ahead of the PFAS compound, which is their functional head. So that's that, little box that I'm showing there. And then on the right side is the PFAS compound itself, that longer rectangular box. So the functional head is something that's actually almost biodegradable in a sense. It's something that will go away over time, but it's the PFAS compound itself, or the molecule, that will remain, you've heard the term forever chemical, right? It's something that lasts for a very long time. So how you can almost think about it in a sense is if you were to consider, and I took this example actually from CDM Smith in a presentation that I saw, almost 2 years ago. But what they did is they related it to an arrow. So let's say a battle took place, 1,000 years ago, and 1,000 years later you walk up on site. You're not going to see a field flooded with a bunch of arrows after the battle took place, right? The flute and the shaft is going to be degraded. It's going to be gone, just as you would expect the precursor aspect of PFAS to be gone, right? It's degraded, it's done with. But what you may find is the arrowhead itself, the stone aspect of it. So the stone arrowhead aspect of PFAS, of a precursor plus PFAS compound, is the PFAS itself. So that's the arrowhead. Now, another thing that kind of relates to an arrow in general, and specifically an arrowhead with PFAS, is the amount of barbs that the arrowhead has itself. So PFAS consists of carbon-fluorine bonds. It's what makes it a forever chemical. The carbon-fluorine bond is the hardest thing to destroy, or one of the hardest things to possibly destroy in organic chemistry. So that's like the stone aspect of the arrowhead. Now, the more carbon-fluorine bonds that you add, the longer the chain. So here in this picture, I'm showing, the black dot with the red, or with the green dots. That's, a 6-chain PFAS compound that I'm showing. So, PFOA, PFOS, those are pretty common types of PFAS compounds that you may have heard before. Those at 8. So that's actually considered a long chain compound. So that could be almost considered like an arrowhead with a lot of barbs. And, the reason why you'd have multiple barbs on an arrowhead is when you shoot something, it's going to stay within the target longer, right? It'll be harder to remove. When we consume PFAS, like long chain compounds in our water supply, that's actually how it's sticking into our bodies. It's sticking into us when we drink it, in water or whatever, as if it were an arrowhead with multiple barbs because it's long chain. The long chains make it stick longer. So it's all bioaccumulation when we're consuming these things, especially long chain compounds. Some of these won't go out of our system until for decades. So the longer the chain, the longer it's going to be retained in our body. So when you see proposed regulations out there, a lot of those are going to revolve around longer chain. Now, that's not to say that short chain isn't something that's also a concern. It expels out of our bodies maybe in 1 to 3 years or so, aka less barbs, right? Less, less carbon fluorine bonds. But the fact of the matter is we're in a situation now, in the U.S. and globally even, where this is in our water supply and it's a continuous flow of consumption, right? We're expelling it out, but we're taking it in just as much, if not even more, right? So that's the problem that we're in. And there's 15,000 different types of PFAS compounds and species out there. So there's just a lot of it that we're dealing with in terms of removal and prevalence. Some of the issues that we're seeing, across the US and everywhere, reproductive issues because of PFAS, developmental issues, issues with even fighting off, diseases and immunity deficiencies. Various cancers are all linked to PFAS and what we've been seeing from PFAS. And in particular, to give you an idea of what is loaded with PFAS in terms of products, food packaging at 15 million parts per trillion. I was actually pretty astonished the first time I saw that how much food packaging contributes to that. And then also cosmetics too. Carpets. When I talk about the qualities of PFAS and the hydrophobic aspect of it, it kind of makes sense why carpets is in there. Carpets is a big portion of it too. And kind of how I think about it is when you pour liquid on a carpet, or if liquid spills, you might see it kind of hovering on the top. To me, whenever I see that, I think it's PFAS almost at work. It has the hydrophobic aspect that's keeping the water from soaking in a sense. So that's kind of at least how I see PFAS in action. And again, it will make more sense in the next slide or two. But it's products like that that have that hydrophobic type of resistance to it. Teflon, even jackets, water resistant type of jackets have PFAS. So all these different types of products that, unfortunately for us in landfills, we're the ones that have to deal with the problem because that's where it's all going, right? So we are the recipients of this problem, and we're left to be the ones to deal with it because it is the largest, one of the largest point sources, the landfill itself. In terms of federal regulations and what's kind of being done right now, so you have EPA CERCLA Superfund. So the thing about what's going on with Superfund in this is, in order to be violating Superfund Act, you have to have over 1 pound of PFAS that's basically being released from your facility, which you're never going to find, especially for a landfill. I mean, we're talking about to the tune of parts per trillion, right? Parts per billion, even. We're not going to get to the pound. So I mean, in terms of CERCLA and having that be some sort of regulation that we need to follow right now, it likely won't happen, right? For RCRA, there is 9 PFAS compounds. The thing is, to be subjected to RCRA, because all these are hazardous constituents, they're not hazardous waste yet, you have to be under RCRA corrective action at this time in order to be subjected to dealing with those 9 compounds. So that's something that most sites likely won't see either. EPA Plan 15 is basically a effluent limitation guidelines. They're being developed, basically trying to figure out kind of the path forward for discharging to surface waters and kind of getting regulations around that with respect to PFAS, but it's still in developmental phase. I know there is a Plan 16. There was an article, I think, a few weeks ago about the development of that, but I still think that there's a lot of work to be done. What I'm showing on the right is a map of the U.S. from the site called Safer States. And this is actually a pretty helpful website. If you're interested in checking it out, it gives you an idea of where various states are in terms of adopting regulations and introducing various PFAS regulations. So it's a pretty powerful tool. With respect to Wisconsin in general, some of the things you may have heard of or seen is DNR has done quite a bit of research from monitoring various wells, be it groundwater, landfills, wastewater treatment plants, and drinking water treatment plants. So they have an idea of data of what sites have PFAS and what are problems, what are and what aren't problems in a sense, at a very high level, I'd say. And there have been a lot in the news in terms of cities that have been plagued by PFAS. That list there, Wausau to name one in particular. Eau Claire seeing a $20 million lawsuit. Attorney General in particular has a class action lawsuit out there for basically all PFAS providers, manufacturers. So be it JCI, 3M, all those guys. There is lawsuits out there. Town of Campbell class action lawsuit with 58 impacted wells. So a lot kind of going on in the state, and I'd say more to even come. So now I'm going to pivot a little bit to what foam fractionation is in a sense, but a little bit about Water and Carbon Group. So we've been around since 2007. We're an environmental services business. The picture I'm actually showing here is of a site in Darwin, Australia. This is the Shaw Bay facility, which is a landfill. So this project in particular, this was in 2017, it asked for the treatment of ammonia, TN, and then PFAS as well. So in 2017, we had a response for ammonia and TN. So I'm showing some SBRs along with an MBBR for TN removal. But the leaf or the foam fractionation aspect, or I guess the PFAS removal aspect, is something that we didn't really have at that point in time. So we kind of assessed what we knew about PFAS in general. We know that PFAS is a surfactant, right? So knowing that it is a surfactant and how people got rid of surfactants in the field in general, even in various industries, was using the process of foam fractionation. So foam fractionation isn't something that's a new technology that, has just began to exist because of PFAS application. It's something that's been around in the oil gas industry and in industries for decades, for the removal of those surfactants, right? So we knew that evaluating foam fractionation was a good start to our hunt for removing PFAS at this facility. So that research began in 2017. And then by 2022, we had the first leaf foam fractionation system developed at the Shaw Bay facility. And, since then, we've been actually under contract for 5 PFAS compounds at this facility and have been achieving non-detect limits since. That's actually the longest running fixed PFAS foam fractionation removal system on the planet at that Shaw Bay facility. So I like to think in terms of acquiring data and understanding the PFAS process. And we're going to have more than anyone else out there. Fast forwarding to 2024, we have a facility in Bethlehem, Pennsylvania in July. This thing was up and running. We've been achieving non-detect for 5 other PFAS compounds since that's been in operation. And I'm going to get into some more detail on that a little bit later on. But about the theory of foam fractionation itself and how PFAS interacts with it. So I mentioned the functional head a little bit in precursors in some detail. I'm going to point out a different definition of head of the compound here. So if I were to speak about PFAS in general, not talking about the precursor, but just the PFAS compound, there is a hydrophilic head to that, and then there is a hydrophobic tail. So if you were to consider what the interaction would be of a PFAS compound on, let's say, a bubble, you're going to get an attraction from the hydrophilic head on the exterior of the bubble, being that the liquid phase, right? The hydrophilic head is attracted to the liquid phase. Then the hydrophobic tail, that carbon-fluorine bond that I mentioned, that sticks, right? The big part of the problem, is attracted to the gaseous phase of the compound. So it's an amphiphilic particle. It has both of those hydrophilic and hydrophobic qualities. But if you were to put PFAS into a reactor like the one I'm showing, a fractionator, I use the word reactor and fractionator pretty interchangeably, but if you were to consider what PFAS would look like in that fractionator, it wouldn't be submerged or anything like that. In fact, what it would be, as I mentioned it being a surfactant, is it would all be at the surface. So what you would actually get is the effect of a bunch of what I like to call as hydrophilic headstands. So you get the hydrophilic head touching the liquid phase, the hydrophobic tail sticking up in the air, and you're going to have a major bulk surface concentration at the surface because you have a lot of PFAS in your leachate. And what you're doing when you have a lot of disturbance on the surface and you're having a bunch of hydrophilic headstands occurring is you're getting a major reduction in surface tension. So we all know water has really strong, or it's a high surface tension, right? When you have a bunch of surfactants or things on the surface, you're breaking the surface tension. You are greatly reducing it. So that kind of gives you the freedom to, let's say, all right, if I were to add foam fraction, or if I were to add fine bubble diffusers to the system, a bunch of microscopic bubbles, I'll be able to create foam very easily now because I don't have to deal with the higher surface tension of water. In fact, you create it so easily that it creates the perfect transport mechanism for PFAS to be lifted up and out of the system. Why? Because just like the bubble, right? With foam, you're satisfying the hydrophilic aspect of it from the interstitial liquid of the foam itself, kind of like the outside of the bubble. But you're also satisfying the condition of the interior of the foam, which is the interior of the bubble, right? The gaseous phase of it. So because of that reduction in surface tension, you have the easy creation of foam. You satisfy both conditions of the PFAS compound. And basically it's that positive pressure in the fractionator that drives the PFAS up and out of the reactor into that dotted line cone that I'm showing, which is the foam collection hood. So that's how PFAS interacts with the process itself, how it's driven out of the system. Now, per fractionator, you have about 2 to 4% of the volume basically removed per fractionator per step. So if you take your flow and multiply it by 2 to 4%, that's the amount of foam that you're basically getting out of the reactor that it encapsulates the PFAS, right? Now, there's about 3 phases in this process. There's 3 stages and typical for our designs. I'll get into that in the next slide. But before I do that, one other thing I'm going to mention. I talked about long and short chain compounds earlier. Long chain compounds will take less hydraulic retention time in a sense to be removed out of the system. So if you take PFAS, PFOA, for instance, the 8 carbon chain that I mentioned, that'll be about 14 minutes worth of time, hydraulic retention time or so, to be removed out of the system. If you take into account, let's say, a short chain compound like PFHPA, which kind of rides the line on short and long, but let's say it's PFHPA, that's about 22 minutes worth of hydraulic retention time required to be removed out of the system. So it's going to take you more time or more opportunity required to remove short chain compounds as you would long chain compounds. And the reason for that, I kind of think of it as almost like a fight for competition in nature, in a sense. So I mentioned the 3 stages. You have stage 1, stage 2, stage 3. Stage 1, you have all of your PFAS compounds, be it long and short, in there. But the thing is, when you're trying to fight for surface area space on bubbles, or foam rather, your long chain compounds are going to take up that space a lot easier because the longer tail than the shorter chain compounds. So it's I kind of think of it as almost like nature in a sense, right? The bigger one wins out in stage 1. So you're going to get more removal of long chain compounds in stage 1. Now that most of the long chain compounds are removed in stage 1, you can move to stage 2. Short chain compounds have more of an opportunity to take up that surface area space and be removed. Then you move on to stage 3. It's like a polishing type of step where anything left over has a chance to be removed. Now, particular in terms of hydraulic retention time, we provide in our designs about 30 minutes worth of HRT per reactor. So that's 90 minutes worth of HRT opportunity for PFAS compounds to be removed, which is a lot of time. We purposely do that to give as much possible opportunity for removal without adding any type of supplements or anything needed for the process. So we really try to emphasize, bigger, better in terms of HRT and removal for foam fractionation. I mentioned again the 2 to 4% of residual, or I guess of foam that's created per reactor, right? So 2 to 4% of the total flow per stage. That 2 to 4% is taken on to another part of the process. So the 3 stages that I'm showing here is the primary aspect of foam fractionation, but there is a final stage. So this is just a 3D rendering, but if you kind of look at the fractionator in the middle right side-ish of the screen, that's stage 1, followed by 2 next to it, followed by 3, and then the 4th one that's a little bit cut off on the screen is the foam concentration step. So the first 3 of the primary stage, the foam concentration step, is the one that's cut off a little bit. That 2 to 4% of the total flow, essentially, so that it goes to the lighter gray tanks just across the walkway there, and then it goes, it breaks down, as foam into liquid. Then that liquid is pumped back into the foam concentration step. That foam concentration step, when all said and done, brings that total flow down to about 0.1% in total. So when all said and done, you're left with 0.1% of the total flow. That is your basically leftover volume that has the PFAS concentrated in it. A few other things that kind of point out, that's a a pump skid and blower that I'm showing there as well, and then that's a leachate tank that's almost like a buffer tank in a sense that basically feeds from the pond or the raw leachate tank. But I'm going to show you a real actual picture of what it looks like inside a building in a moment, which is actually from our Bethlehem landfill. So Bethlehem landfill is the site I'm going into some detail on and give you a real perspective on what a leaf system actually looks like. So here we're doing anywhere from 50 to 100,000 gallons a day of leachate treatment with our foam fractionation system. We're doing about 14. They do about 1,400 tons per day of waste. It's a municipal solid waste landfill, and it's a waste connections landfill. So should do quite a bit of work with waste connections as well. So you'll in the future see quite a few more of these. What I'm showing here is kind of the beginning phases of that project. So this was an old waste to energy site that Waste Connections had at the Bethlehem site that was no longer being utilized. So we kind of took it as an opportunity to use this space. So kind of what I'm showing here, where what sits now is a trailer or an office for the operator. And then the building that's sort of cut off on the right side of the screen is a 60 by 30 building that again was no longer being utilized, but now houses the leaf system. So a bit about what went into that project. In the bottom left, showing the creation of the secondary containment. All leaf systems and all foam fractionation systems absolutely should contain secondary containment. We take that very seriously, safety and precautions. I think typically by standard, we do about 150% for secondary containment of our largest tank. But again, that can be adjusted to be larger if needed. What I'm showing in the image after that is the creation of the walkway and the mezzanine platform. It's not something that's required for installations, but it's kind of a nice to have. You can see the the creation of foam. You can access the hoods as well should any maintenance be needed. But when you're running a process for a while, you kind of get a good feel for what good quality foam looks like when you're running this process. The next picture I'm showing is foam fractionator 1. It's right by the entryway when you walk in. And then the final picture on the right is the leachate line connection point. So there is a raw leachate type of buffer tank in the facility or in the building. The connection point between their 500,000 gallon super blue tank and that tank is basically what I'm showing there. So in terms of the project overview itself, what to expect for a project, or at least how this project went down, was regulatory state POTW approval took an immense amount of time. So really just what I want to kind of show here is to get that going as soon as possible, just because you could be playing the waiting game for a while on that. In terms of project milestones, though, I mean, typically about 2 to 3 months per major milestone. Even the clear water operation aspect of it didn't take that long. We just decided to run clear water for as long as it took to get the regulatory state and POTW approvals finished. So what it looks like in the building itself. So what I'm showing here is foam fractionator 1, followed by 2, 3, and then the foam concentration step. And then there is the pump skid again. There's a little walkway underneath there, underneath the mezzanine walkway as well, to access the fractionators if needed down below, and then again as well up top to access the hoods or just to even observe the creation of foam. If you are standing where that picture was taken and then turn your body to the right, you'll get another look at the pump skid, as well as the blowers and the raw leachate tank. If you were to walk on the left side of the pump skid, you would kind of walk right by the PLC too. So the PLC is in there too. To give a little bit of an idea of what data looks like in general. And this isn't even specific to the Bethlehem site. I just kind of took 34 data points for what is pretty common to see in terms of PFAS. At least what I've seen is pretty common nationwide. PFOA, PFAS, PFHPA. Really, the point of what I want to show you here is you can even take the large variance of, let's say, PFOA. It's at that 17,000 parts per trillion mark. Average is at 6,000. No matter where it's at, we're going to hit limit of detection. So LOD, by using a 1633 method, which is kind of the gold standard, is about 20 parts per trillion, I'd say, at worst. You could, do better than that in a lot of cases, but it's very much relative to what your general chemistry is for your PFAS. That just kind of dictates the amount of inhibition, the amount of dilution that the lab needs to take, and then from there you kind of back into whatever your limit of detection is, right? So, but I'd say at worst you'll be at about 20 in terms of LOD. And to give you a little bit more perspective in general on what we do for PFAS compounds, this is 18 PFAS compounds that I'm showing here. The 5 that I mentioned for the Shaw Bay facility in Darwin, Australia, as well as the 5 that I mentioned for Bethlehem Landfill in PA, are listed within this table here. We're achieving non-detect for all of those. So I won't tell you exactly what it is, but I can give you a hint, I guess, by saying that. We're achieving non-detect for all of those compounds that are listed. You can see for long chain, achieving non-detect is really easy, and short chain for very short chain compounds, we're achieving non-detect. It does, however, get a little tricky with XA, EA, BA, and BS. But we do have an added co-surfactant that we add to that to make it a little bit more of improved removal efficiencies. So although some of those short chains can get a little bit tricky, we can still get pretty good removal. And I could tell you that there is a WCG2 chemical that we're getting pretty close to launching. I can't quite do it yet, but it certainly is an improvement on this as well. So you may have heard before, in other types of technologies for PFAS, you may hear things like, foam fractionation can't remove short chain. That's definitely not true, at least with respect to what we've been doing, at Bethlehem and other places as well. A bit about residuals. This is one of the main questions that we get asked a lot is, like, okay, great, you can do about 0.1% of your total flow, and that's your residual left over. But what do you do with that concentrated PFAS as a liquid? How do you go about dealing with it? Which is a great question. What we do at Bethlehem actually is, so that 0.1%, we actually apply an organoclay to it. So that 0.1% that is concentrated PFAS liquid, we add organoclay to solidify it, and that actually brings that, 0.1 times Q down by even further reduction by 10,000 or even 20, we've even seen up to 21,000 reduction on top of that. So we're bringing that liquid really drawn down into a small solidified state at the very end. So by adding our modified organoclay, we can really bring that down, drive it down further, and provide a little bit more peace of mind by making it in the solidified state. Although that there are landfills out there adding just the leachate back directly in as liquid. In fact, we were doing that before we fine-tuned our organoclay at the Bethlehem landfill site. And there is some pretty good data on sequestration, but I do know that there is a lot of landfills also that are uncomfortable with just the premise of bringing it back into the working phase as a liquid or in general, right? And I can completely understand why, right? But that is something that you can do. If that's something that you're not interested in doing, then permit destruction is another option as well. So be it ECO, SCWO, and halt processes, foam fractionation pairs with any destruction technology. In fact, it's basically required to have foam frac with any type of destruction technology that you run with, because the goal of the destruction technology is, do destruction on the volume that's presented to it, right? So if you go to destruction technology, or if you say I want destruction and I have 50,000 gallons of leachate to treat, you're not going to do destruction on 50,000 gallons. Your OPEX is going to be way too high. The energy cost is going to be through the roof. You need to bring that volume down, which is exactly what foam fractionation does, right? You bring it down to that 0.1% of Q. So, the less volume that you have to destroy for destruction, the lower your OPEX. So there really is no circumstance out there where you can do destruction without foam frac. Unless you have just straight up concentrated AFFF in a storage tank or something like that, but it is required to have, or at least you need a way to bring the volume down, right? And I can tell you that, we've worked with basically all destruction technologies out there. Our concentrated foamate is like gold to them. So we've shipped this out and had them experiment on, destruction with their system. So, we've worked with all different types of destruction techs. Offsite management as well is something that could be an option if you have access to deep well injection. Not everyone will have that access, but of course it's another alternative. In terms of CapEx, so if you take, let's say, a range between $20 and $35, and if you were to say I need a system that does about 40,000 gallons per day of treatment, that comes to about 40,000 times 35 on the higher end of the spectrum is about 1.4 million. Now, I'd say roughly that gives you a rough idea in terms of budgetary costs for 40K system. As you go up in treatment capacity required, you can go down. It's a sliding scale in terms of per dollars installed for gallons per day. So you get to 100 or whatever, you might use the $20 value, and it'd be roughly about 2 million, right? So it's not a perfect idea of giving you costs, but it gives you a rough sense of what that CapEx would be. Air treatment systems are also offered as well. So there's one exhaust on our leaf system. And what we do is actually just provide a vapor phase carbon filter scrubber on that. And its range is kind of based on capacity that you're treating, but I'd say roughly about that 150K mark. Not every site would even require it. Like if you're talking to anyone in New York, you're going to have it just because New York has pretty strict air treatment or air quality standards. But again, not something that you need to have, but it's something that we do offer. Residual treatment, I'll get to that on the next slide about OPEX. And in terms of buildings, it kind of depends on building size and system size, but I'd say anywhere from that, 250, 350 mark. That's for a pre-engineered metal building. So that's not including, foundation or anything like that, but should just give you a rough sense. And just one thing to mention too, the example that I gave, with Bethlehem, it's 60 by 30 building. It's a fixed system. We have fixed systems, in Australia too. We don't have to offer a fixed system. We do have mobile designs as well, but from being in Wisconsin, particularly, right, the winters can be harsh. Tends to be better working out of a fixed system. So it is something that we, encourage in a lot of places. For OPEX, low energy, the leaf system is the low energy evaporative fractionation system. So we definitely hold true to that. So it's about 4 watt hours per gallon. So if you take that and apply your kilowatt hour cost from your energy bill, it can guarantee you're going to get low energy usage. No use of chemicals. So one of the nice things about foam fractionation, the beauty of it is it targets at the surfactant itself. So, I mean, leachate being as nasty as it is, we've done, we're successful in doing this with RO concentrate too and pairing with RO. We're not fazed by the nastiness of the leachate and everything that's in it. You don't really need to add chemicals because, again, we're targeting strictly at the surface level, which it does a really great job of doing. So you don't really need to add any chemicals, from the harshness of leachate or of general chemistry. Maybe you have scaling potential, but that's kind of a different story, right? You don't want to have scaling in your piping. In terms of short chain removal, if you were to add WCG1 chemical, which we've been basically yet to see a need for in terms of regulations that we've seen out there, but should you find that need, it'd be in that thousands of a cent range that I'm actually even showing for low residual. So it's not much to add chemical if required. For low residual itself, that organoclay that I mentioned, that's what you're looking at, per system gallon as well. Now, I want to give a little bit of context on what your first step might be in a project. So what we have out there is our treatability study trailer. It's our leaf demonstration 1K unit. So we have 2 of these circulating around the US now, and it does 1,000 gallons per day. And it's really simple. We roll it up on site. Basically, a pickup truck pulls it around, and wherever you find a good spot or tell us to drop it, we put it there along with secondary containment around it. And then we run a 5-day test. We'll tell you kind of what the performance looks like for PFAS itself or for foam fractionation itself. Give you an idea of how it operates. Operators like seeing how it works so they have firsthand experience on operation should full-scale something or systems be something that they're interested in. This does a really good job of emulating a full-scale design, so it does really give that experience. We've tested this on multiple different types of complex waste streams, be it digestate, be it RO concentrate, leachate, of course, groundwater, various industrial applications. This has been battle tested on multiple different types of streams and has been very successful in doing that removal. So kind of wrap up in summary. So I mentioned hydraulic retention time, HRT. I see HRT as opportunity for removal, right? How much opportunity are we going to give for removal for our leaf system? We like to give 90 minutes worth in our designs, which is a lot of chance for as much removal as possible. Fixed plant designs is something that we emphasize in a lot of cases. I'd say even, again, specifically to Wisconsin, it can be kind of brutal being an operator having to work out of a mobile system and something that might be seen as temporary in a sense. I can tell you they appreciate it in PA, having a fixed system. And even from a maintenance standpoint, much better to go with a fixed system in that case too. Some of the mobile systems can get a little crammed and almost kind of put it as trying to do work between the back of a refrigerator and a wall, right? You're really crammed. You're not going to be able to do too much or be very difficult for you. So to even change out a pumper or blower, it's going to be a lot easier to do in a fixed system. And even from a safety standpoint in that case too. Automated controls. Again, I'm not bashing mobile systems by any means. We offer mobile as well, just kind of giving what we've seen out there. But from an automated control standpoint, be it remote monitoring, whatever the case is, it's a pretty simple design to automate and to run. And in terms of various different types of operations packages, the Bethlehem PA facility is actually ran by a water and carbon group employee, but we offer multiple different types of packages from an operations standpoint, be it having one of our own run the system or doing training for existing staff. We do either type of approach. And from a solution capabilities and flow and capacity standpoint, anywhere from 1,000 gallons a day to even up and over 500,000, right? It's a modular system, so the more that you want to treat, the more we can tack on. So we can go even beyond 500,000 if needed. All right. With that, I think it went a little long. Could take some questions. If you guys have any?
Awesome. Thanks, Chris. I guess I have one question. Is it like a batch treatment system?
So it's a continuous flow type of system, yeah. So it's all continuous, but the batch aspect of it would be the residual aspect of it. So when you have the concentrated PFAS, you're going to be, basically what we do at Bethlehem is we fill up a tank with liquid, we add the organo clay, and until we have that, sealable tank filled with solidified PFAS is when we'll put it into the working phase. That makes sense. But it's a continuous process. So if you're hooked up to a, you're lined into a wastewater treatment plant or wherever the case is, it's going to continue on and the treated flow is going to continue.
Okay. Any other questions?
Well, all right, guys, I appreciate it. Thanks for your time.
Awesome. Thanks, Chris. We appreciate it. And if you guys have other questions, his information is on the screen, and I have the video recording available. I'll probably send it out. We'll have it posted on the Arrow membership page, and I'll work with Swana to see if we have anywhere to post it there.
Fantastic. That'd be great. Thanks for recording it. And thank you guys for attending. I appreciate it.
Yeah, thanks again, Chris.
Yeah. And yeah, let me know if you have any questions. Feel free to reach out.
Perfect. Sounds like a plan.
That's good.
Thanks, Chris. Thanks, Abby.
Thanks, everyone.
All right.
Have a great
Thank you
night.
guys.